options where the first word is the most likely, it's 50%, and then the second one is 1/3, and the third one is 1/6. This adds up to 1. Gives you 1. And this. But let's now say that you split this up. So maybe the first word is, or one of these words isn't a word but a phrase. It's actually two words. So you would like to have a measure that doesn't depend exactly on how you cut your sentence into words or into phrases. So that means if you like say a phrase like is a, your information content of the sentence shouldn't depend on whether you count is and a as independent events or is a as a combined event where you have a different probability. So in this case, you could have, instead of one event with three different probabilities, you can have two events where the first event has two options with equal probability, and the second event has two options with 2/3, 1/3 probability. And if you work this out, that means that this option is 50%, and this combination is 1/3, and this combination is 1/6. So in the end, you have three options which have the same frequency as these three options. And you want your information content to be the same in either case. So if you have, and let's call it h, of this set of probabilities, that should be the same as the sum of the information content of these two events that lead to the same outcome. Because you don't know exactly which events went into getting the outcome. What's not clear? Let me think. Let's try to break it down. So this first part, this is okay? Okay. So now, because when we're observing, we can take this back to alignments where each of the we don't know the events. We don't know this structure. We only know the frequencies of the different outcomes that we get, right? So we can say we have 1/6 phenylalanine. Let's make it. I'll make it have the same frequencies. So there's what's that? 1/3. We have 1/2 tryptophan, and we have 1/6 phenylalanine, right? Now we're counting the outcome, but you could also, if you know which mutation events happened in the evolutionary history to get this outcome, then the probabilities of these mutation events combined should give the same frequency as the amino acids that you have in the end. Yeah. So because like these three amino acids didn't happen in one event, like this situation suggests. So it was actually two steps, right? So there was one, yeah. So maybe there was a tryptophan first, and then it mutated into an alanine, and then in one case the alanine mutated into a phenylalanine, right? So you get the same outcome. Half tryptophan, 2/3 alanine, and 1/6 phenylalanine. But you can also count it as these two independent events that led to this outcome, right? So you can look at the outcome, and then you have this information content, or you look at the events that lead to the outcome, but it should be the same. That should have. There's no difference in. There's only more sort of structure in it, but it's the same thing. But so if you measure them independently and you add them up, you would like to have a measure that comes to the same outcome here, to the same value of the information content in the events that you're measuring. Yeah? Thanks. Okay, so, and I'm not going to go through the derivation. There's a very nice paper there. I should have, of course. Did I have the link on the? Oh yeah, the link is here. So if you want to look it up, the derivation is in there. Yeah.
So around the arrows, there are chances, and the last
yeah.
part not, because the last part should be one, right?
Which last part?
A half, 1/3, 1/6, on the right side. The last three numbers. Why wouldn't that be one when you say that?
This adds up to 1. These add up to 1.
But the last part not.
And these half plus 1/3 plus 1/6 adds up to 1. 1/3, 1/6 plus 2/6 plus 3/6. A half is 3/6. A third is 2/6. 1/6 is 1/6. If you add up 3/6 plus 2/6 plus 1/6, it's 6/6 is 1. But you're not the only one who doesn't see this. From anecdotal evidence, we think that most people in computer science don't immediately see that this adds up to 1, and most other people do. I don't know why. Different way of looking at things. Yeah, you're with us again.
Yeah.
Good. Who has the time? I don't know what the time is. I have no clock. My
1:04.
Okay, we have 10 minutes left. Good. Right. So I won't go through the derivation now, but the formula that he came up with, which he can derive from the requirements that he had. So actually, I didn't list all the requirements. It should sum up to 1, and a few other things. Oh no, sorry. The probability should sum up to 1. This is the formula that he came up with. So if you have n events, n options for an event, and the probability of each of these options is pi, then this is your information content of the set of outcomes for the event. And it's 0 if there's no choice, and there's no choice if there's only one p that is not 0, which also means that it has to be 1 because they have to add up to 1. And the example I always use is if you have elections in a country with an authoritative regime, then there's usually there's elections, but there's only one guy you're supposed to vote on. There could be even more candidates, but you'll probably end up in jail if you vote for any of the other ones. So then there's one option, and then there's not really much information gained from having the elections. It's very easy to predict what the outcome will be. I'm not going to give any examples of countries, but you can probably think of a few. The other extreme is where the information content is highest, is when all probabilities are equal, which happens a lot in Europe and also in the American election, well, to some extent in the American elections, where in the polls all the candidates have roughly, or there's a big set of candidates that have roughly equal probability in the polls. Then you really don't know what the outcome is going to be. Yeah? So then there's a lot of information gained from actually having the elections, because then you know who's going to be get the highest probability. Okay. So this is just summing that up. So if you do this for bigger numbers, so now we go back to the alignments, right? And now we go. So the tricky. So how do you now come from? There's a different way to get to the information entropy, and that's to continue the story that I started here, because I haven't connected these faculties up with the Shannon information entropy. And one of the tricky things is that if you have, this is a very small alignment. If you have a decent, not even a very big alignment, but this is, I forgot, 23 or so, 33 sequences, then there's already, there's about 10 to the 23 different options to get a mixture of 4 amino acids. That's not even completely unconserved. Yeah? So these numbers are awkward to work with, so you would like to have a slightly more convenient way to do that. This is what I already did on the board. Yeah. So we can actually go, and here I use S, but in the previous slide it was H because Shannon used H for his information measure. But there's a different way to do this, where H is the logarithm of omega, and omega is actually our number that we calculated here. So, oh, that doesn't work. Yeah, so it's the number. It's called the number of realization states. So it's the number of ways in which you can get a certain outcome. So if I go back to the original example, where it's a conserved tryptophan and there's only one way to get it, then you have the omega is 1, logarithm of 1 is 0. So your information entropy, your information content is 0. That's because it's a conserved tryptophan. So you're not surprised if the next sequence is also a tryptophan. There's nothing new that you've learned from looking at the next sequence, because it's going to be a tryptophan, you know that. Whereas here, every new sequence is going to bring you more information because it's uncertain. Yeah? That's the way to look at it. Okay, so you can calculate this omega by what we already did. We take the faculty, but now it becomes a little bit more complicated if you do it properly, because you need to take into account for the number of different. So if you have 6 different ones, it's easy. It's the faculty of 6. But what if you have an alignment of 30 and there's a mixture of 4 different amino acids? So you have 10 of one and 5 of the next, and so on. Then you have to take into account the fact that if you have 5 of the same ones, it doesn't matter in which order they are. Yeah. So this is what is the sum over x of nx? So x's are different amino acid types. So what is this sum of? What is this sum then? I'll take this example again. A and F. So if x's are different amino acid types, what is n of x? What is n alanine? It's a bit noisy here, isn't it? What is the n alanine? 2, right? There's 2 alanines. And the n of phenylalanine. Oh, I have them here. Oh, it's the other way around. Yeah. 2 alanines, 3 tryptophans, and 1 phenylalanine. Yeah. So what is the sum of n? 6, right? It's 3 plus 2 plus 1, but it's just the number of sequences in your alignment. Yeah, this is a constant. But this is our 6 faculty that we had originally. But now, here we have the faculty of x. Okay, I'm going to write this out. So we have 3 plus 2 plus 1 faculty, right? That's the top line in my formula over there. And then, but there's 1 tryptophan, so that's easy because it's just going to be 1. But then there's 2 alanines, and the first alanine can be here, or it can be there, and the second alanine will be in the other place. It doesn't matter if you swap these 2 alanines. So there's two options to put the alanines here that we don't care about, because they're going to be in the same place. So that is actually, so you divide this by the faculty of 2 to account for the number of ways in which you can rearrange these two alanines. Now we have 3 tryptophans, which you also can rearrange. How many rearrangements of 3 tryptophans are there? There's 3. Faculty of 3, right? There's 3 places you can put the first tryptophan, then there's 2 places left to put the second tryptophan, and there's only 1 place left to put the third one. So that's 3 times 2 times 1. So that's the faculty of 3. And then just to make it complete, for the phenylalanine there's only one option, which is actually the faculty of 1, because there's only one place to put it. It could have been 5 tryptophans, then there were more sequences, and then there were 5 faculty ways of reorganizing these 5 phenylalanines. Yeah? So this is 2 faculty times 3 faculty times 1 faculty to account for the fact that we have a couple of similar symbols and we don't care about how we rearrange them. Yeah? So this is all the total number of arrangements that we can have, and these are the ones that we don't care about because they're the same symbol. Now this pi means product, and so this is the faculty of all the x's, the numbers of the different amino acids, and the product of those. Yeah? So this is exactly the same. So now you can calculate that. So this works. It's just inconvenient that you first have to calculate these huge numbers and then take the logarithm of them. So the final thing that we do here is there's a very nice approximation, is that you take for the logarithm of a faculty, which you can approximate with, so the logarithm of the faculty of x is, to a fair approximation, x times the logarithm of x minus x. And it doesn't work for small x's, but since we're interested in alignments with fairly big numbers of sequences usually, this is a very good approximation for us. If you work this out, and I wanted to do that on the board, but I don't have time for that anymore, so you can actually, you can take this one, you have to put in the fact that you have to go from numbers to probabilities, and then you can work out that this, using this formula with that approximation, gives you p log p minus p log p, the sum of p log p for all the I. And here the x. So here the x is again the different amino acids that you have in your column. So this way we can actually measure the amount of information content in an alignment column, which actually correlates with the or anti-correlates with the conservation. But now you understand why, because the situation in the one that I gummed out here, where they're all different, there are just many more ways to get that. So that's least surprising from an evolutionary standpoint. This one, which has few options, is actually very hard to get. So if you get it, something must have happened. Yeah? And we all know what that is, what happened here. Well, random outcome is also the result of evolution. So what? This is the conservation is what we observe. That's the result. So what happened to get conservation? It's a functional location. That's the reason why it happens. But what happened? Sorry? It's selection, positive selection, right? The reason that this happened is that because if you put anything else here, then a tryptophan or a phenylalanine or an alanine, this is a very unlikely example, but let's put a tyrosine here, then they're all aromatic. If you put anything there except an aromatic residue, you break something, which leads to a decreased survival chance of the organism in which this sequence happens to be. Yeah? It's like a car. If you paint it in a different color, it still drives. If you take out all the seats, it's uncomfortable, but it still drives. It won't sell as much. If you take out one wheel, it could still drive. It's very inconvenient, but if you take out two wheels, you're done. Yeah, it's not going to fly. It's a car, it doesn't fly. It's not going to drive. So that's what happens here, right? You don't see cars with two wheels. Not because you can't make them. They exist. They're in the junkyard. You don't see them on the road. Yeah? Okay. So that's positive selection. I think with that, we've come to the end of part 1. Thank you very much again for being here. I think the weather couldn't have been better on a random week in September in Amsterdam. We'll continue in the main building in 08A00. Yeah, 8th floor and the big lecture room. Thanks.
Thank you. Thank you.
Yeah.
La raya.